Good day, everyone. I am Vicar Balili and John Christian Abdon for the Molecular Orbital Theory. Now, before we begin, let's take a look at the learning objectives. Make sure you thoroughly understand the following essential ideas. In what fundamental way does the molecular orbital model differ from the other models of chemical bonding and that have been described in this lesson? Explain how bonding and antibonding orbitals arise from atomic orbitals and how they differ physically. Describe the essential difference between a sigma and a pi molecular orbital. Define a bond order and state its significance. Construct a molecular orbital diagram of the kind shown in this lesson for a simple diatomic molecule and indicate whether the molecule or its positive and negative ions should be stable. Before we actually begin in the introduction of molecular orbitals theory, the molecular orbital model is by far the most productive of the various models of chemical bonding and serves as the basis for most quantitative calculations. In its full development, molecular orbital theory involves a lot of complicated mathematics, but the fundamental ideas behind it are quite easily understood. And this is all we will try to accomplish in this lesson. Instead of seeing bonds as shared pairs between the two atoms, like the Lewis or valence bond theory, molecular orbital theory describes electrons as spread across the entire molecule. Electrons don't belong to one atom or bond, they belong to the whole molecule. Molecular orbital theory explains why some molecules exist and others don't, why oxygen is paramagnetic, and how electrons distribute and determine stability. How do atomic orbitals combine? Chemical bonding occurs when the net attractive forces between an electron and two nuclei exceeds the electrostatic repulsion between the two nuclei. For this to happen, the electron must be in a region of space, which we call the binding region. Conversely, if the electron is off to one side, in an antibonding region, it actually adds to the repulsion between the two nuclei and helps push them away. This way of visualizing a molecular orbital is to start by picturing two isolated atoms and electron orbitals that each would have separately. These are just the orbitals of the separate atoms by themselves, which we already understand. We will then try to predict the manner in which these atomic orbitals interact as we gradually move the two atoms closer together. Finally, we will reach some point where the internuclear distance corresponds to that of the molecule we are studying. The corresponding orbitals will then be the molecular orbitals of our new molecule. We have to take a look at this diagram we have here. This image illustrates how bonding and antibonding regions form when two atoms interact. Here's what's happening in the diagram. The two positive charges represent the atomic nuclei, or the protons, and the negative charge represents the shared electron between these two positive charges. The red shaded area is the middle bonding region where the electron density is the highest. The electron in this region attracts both nuclei and pulling them together. This attraction overcomes proton-to-proton repulsion, holding the atoms in stable bond. The blue areas on the sides are antibonding regions where there is very little to no density. If electrons occupy these regions, as in antibonding orbitals, the molecule becomes unstable because there is not enough electron density between the nuclei to hold them together. The arrow labeled attraction showed the electrons pulling both nuclei inward. The repulsion arrow shows the nuclei pushing away from each other. In short, the red region here, or the bonding region, the nuclei is being held together by shared electron density. And the blue region, the antibonding regions, there is no bonding force and more repulsion is happening. And to see how this works, we will consider the simplest possible molecule, which is the hydrogen molecule ion, which consists of two nuclei of charge 1. and a single electron is shared between them. Now, what's happening here is it's made up of two hydrogen nuclear protons and one electron. Since it only has one electron, that electron must be shared between the two nuclei. How this forms is as the two hydrogen atoms move closer together, their 1s atomic orbitals overlap. This overlap allows the single electron to be found between both nuclei and not just around one. Let me explain why this is stable. The electron between the two nuclei attracts both protons equally, as shown. This shared attraction pulls the nuclei together, forming a bonding molecular orbital. And this region between the nuclei has the highest electron density, making it the most stable position for the electron. What is a sigma orbital? A sigma orbital, the bonding orbital formed is symmetrical around the line connecting the two nuclei. Because of this symmetry, this is called a sigma orbital, the simplest type of molecular orbital. In summary, this shows the basic principle of molecular bonding. When orbitals overlap and electron density increases between nuclei, the atoms become bound together in a bonding molecular orbital, or the sigma orbital. Bonding and antibonding molecular orbitals. You're probably aware that wave phenomena such as sound waves, light waves, or even ocean waves can combine or interact with one another in two ways. They can either 1. Reinforce each other, resulting in a stronger wave, or 2. They can interfere with and partially destroy each other. A roughly similar thing occurs when the matter waves corresponding to the two separate hydrogen ones orbitals interact. Both in-phase and out-of-phase combinations are possible and both can occur. The in-phase reinforcing interaction yields the bonding orbital that we just considered. The other corresponding combination of two orbitals is the out-of-phase, gives the rise to the molecular orbital that has the greatest electron probability in what is clearly the antibonding region of space. This orbital is therefore called the antibonding orbital. Now take a look at this diagram again. On the left we have the two separate hydrogen atoms, in which its own 1s orbital, or the blue regions here. These orbitals represent the wave functions of each atom's electron. When they combine, the orbitals can overlap in these two ways, in phase or out of phase. This leads to two molecular orbitals, one bonding and one antibonding. The bottom one, or what's called here the bonding molecular orbital, the orbitals add together in phase, reinforcing each other, and electron density increases between the two nuclei, or the blue area here becomes larger in the middle, resulting in increase between the two nuclei density. And here we have in the top part the antibonding molecular orbital. The orbitals combine out of phase, meaning their waves cancel in the center. And a node here, a node is where a space between the nuclei forms, or a region of zero electron density is formed. This separation weakens attraction and causes instability or higher energy. In the bonding molecular orbital, this results to a lower energy. As the region holds both nuclei together, electron density increases in the middle. In summary, the in-phase overlap, or the bonding molecular orbital, is stable and high electron density is between the nuclei. The out-of-phase overlap, antibonding molecular orbital, is unstable and a node is formed between the two nuclei. Molecular orbital diagrams. The scheme of bonding and antibonding orbitals is usually depicted by a molecular orbital diagram, such as the one shown here for the dihydrogen ion. Atomic valence electrons, shown in boxes on the left and right, filled with the lower energy molecule orbitals before the higher ones, just as is the case for the atomic orbitals. Thus, the single electron in this simplest of all molecules goes into the bonding orbital, leaving the antibonding orbital empty. Here in the diagram, again, on the sides, each hydrogen atom contributes one s atomic orbital, shown as the boxes labeled H. These orbitals combine to form two molecular orbitals. The sigma, the bonding orbital, or the lowest energy, or the sigma star, the antibonding orbital, or the higher energy. The electron placement, hydrogen ions only has one electron in total. According to the Aufbau principle, the electron fills the lower energy bonding orbital first. The antibonding orbital remains then empty. The bonding strength of this, because the bonding orbital is only half filled, it provides stump stabilization enough to hold the two nuclei together. This stabilizing energy is about 270 kilojoules per mole, making hydrogen ion a real, though short-lived, molecule. Even though it's technically stable, dihydrogen ions are highly reactive. It can even react with itself or other molecules easily, so it doesn't exist under normal conditions. In short, the diagram shows how one electron in the bonding molecular orbital of dihydrogen ions create a weak but real bond between the two hydrogen nuclei. The antibonding orbital remains empty and the molecule exists only briefly because of its high reactivity. Now we'll explain the molecular orbital theory on the second row diatomic molecules.
Hello guys, I'm John Christian Abdon. I'm going to discuss molecular orbital theory of the second row diatomic molecules. Note that only the valence shell orbitals need to be considered because inner atomic orbitals such as 1s are deep within the atom and is well shielded from the electric field of a neighboring nucleus so that these orbitals largely retain their atomic character when bonds are formed. So in bonding, we only need to take a look at the outermost shell or the valence shell orbitals of the element of an atom because the inner orbitals such as 1s is deep within the atom. This rule or note is not included in the hydrogen and helium atoms. Next is the paramagnetic and diamagnetic substances. Paramagnetic substances contain one or more unpaired electrons in their atomic or molecular orbitals. These unpaired electrons generate a magnetic moment causing the substance to be attracted to an external magnetic field. Diamagnetic substances, on the other hand, have all electrons paired. Because the magnetic moments of paired electrons cancel each other, these substances are weakly repelled by a magnetic field. So, now I'm going to show you dilithium. So, an MO theory or molecular orbital theory, we can see here that uh, I've only included the 2s orbital because again we can disregard the 1s orbital because it is deep within the atom. So in the 2s orbital, it gives us one electron on each lithium atom, and that gives us an overall electron count of 2 and 2 electrons to fill the void here in the middle. So first, we fill up the bonding area, which is the area of the orbital that has no asterisk. And the area up here is the anti-bonding area, the sigma orbital that has an asterisk. Uh, and in filling it up, we have two electrons, as I said. So two electrons to fill up on the area here. So we have a bond order of 1. So what is a bond order? The bond order is basically the electrons or the electrons that are paired together or the number of electrons that are paired on the uh, substance. So next, how to calculate the bond order. The bond order is calculated by the number of bonding electrons. Again, the electrons on the bottom, the bottom of an orbital, the orbital that has no asterisk, and we subtract it by the number of antibonding electrons. The electrons in the region up here, or in the region that has, or in the orbital that has an asterisk. So all this divided by a given of 2. So shown here, 2 minus 0, which 2 are 2 electrons on the bonding orbital, and 0 electrons appear on the antibonding orbital, which gives us 2 minus 0, which is 2, and 2 divided by 2 is 1. So it is correct. And next is lithium hydride. So we can see here that we can really just disregard for the uh, 1s orbital, because it, in the bonding of lithium and hydrogen, only the 2s orbital and of the lithium atom uh, is used in bonding. So in bonding this, uh, we have one electron on lithium and one electron in hydrogen. So this gives us two electrons overall, and bond we first fill up the bonding area of the sigma orbital, which gives us a one pair of electron, one paired electron. And again, the bond order, uh, we have two electrons on the bond area, and zero electrons on the anti-bond area, and we divide that by 2, which gives us 1. And this substance here, uh, we can call it a diamagnetic substance, because all electrons on in while bonding are paired. So it is a diamagnetic substance. And if we are going to uh, go higher, or look for uh, higher, mm, uh, bigger atoms, we have to go to p orbitals. And in p orbitals, there are two orbital. We have the sigma orbital and the pi orbital. Sigma orbitals are atomic orbitals that overlap end to end along the axis connecting two nuclei. This orbital is strong and allows free rotation around the bond axis. The bond in uh, H2 is a sigma bond. And pi orbitals, these orbitals form when atomic orbitals overlap side by side above and below the bond axis. This overlap is weaker and restricts rotation. An example of this is the second bond in O2, or double bonds in general contain a pi bond. So uh, generally, sigma orbitals form when sigma orbitals are the orbitals that are connected or joined together, while pi orbitals are still technically connected, but they are side by side. We are shown a bit. I have a diagram here. So sigma orbitals, we can see here that adding a sigma orbital is it shows us that it is joined together with the two nuclei, while pi orbitals are side by side, or uh, above and below each other. So generally, again, sigma orbitals are joined together and pi orbitals are side by side. Uh, It is shown here. And the next substance, dicarbon. In dicarbon, we reach to in the 2p orbital. So the electron configuration of dicarbon is 1s2, 2s2, and 2p2. So first, we go to the 2s orbital. In the 2s orbital, each carbon atom gives us two electrons. So two electrons on each atom gives us four electrons overall. So we can fill up both the bonding area of the sigma orbital and the anti-bonding area of the sigma orbital. So the 2s orbitals are full, and now we move on to the 2p orbital. In the 2p orbital, we are given two electrons on each carbon atom. So the two electrons are overall we have four electrons to join together. So we can see here that the pi orbital is side by side while the sigma orbital is one, which means that it is joined together. And again, we fill it up at the bottom starting from the bonding area, and we have four electrons given, so we fill up with four atoms. So four electrons, sorry, four electrons. So we completely filled up the uh, pi orbital of the 2p uh, orbital. Then next is the bond order. The bond order of dicarbon is shown that it has two, and here's the equation for that. We have six overall electrons on the bonding area, and two electrons on the anti-bonding area. That gives us 4, and 4 divided by 2 is 2. And we can call dicarbon a uh, diamagnetic because it has no uh, unpaired electrons. Basically, all electrons on while bonding is paired. So it is a diamagnetic. Next, the next substance is dioxygen. So we can see here that in dioxygen there are two electrons that is unpaired. So yeah, two electrons that is unpaired on dioxygen. So which means that dioxygen is a paramagnetic substance, which basically uh, means that it has unpaired electrons. So we can see here that again in the 2s orbital, it gives us two electrons each side and fills up the bonding area here, both bonding and anti-bonding area. In the 2p orbital, it gives us four electrons on each side, which has uh, we have eight electrons to fill up on the anti-bonding and bonding area. First, we fill up the bonding area of the orbital, first by the sigma orbital, and then this pi orbital, then again the pi orbital up here, which has two unpaired electrons. And in bond order, which gives us two, because we have eight uh eight electrons bonding on the bonding area, and four electrons on the anti-bonding area. Divided by two, we have two paired electrons. So again, the oxygen is a paramagnetic substance because it has unpaired electrons. So, and that is all. Thank you for listening in. Again, this is the MO theory, a more detailed way of showing you the bonding of two elements. Once again, I am John Christian Abdon with my partner, Vicar Balili. Thank you for tuning in.